Hey guys, welcome. These are your notes for section 9.3, similar right triangles. So we're keeping in the right triangle theme, and you guys know similarity from chapter 8 very well, and we're going to put it together here. So what we're going to learn are to identify similar triangles, solve some real life problems, and a new thing, using geometric means. So the first thing you want to do is identify similar triangles, and it gets a little visually tricky. So let me show you where this comes from here. Um, Theorem 9.6, right triangle similarity theorem. All right, now check out how cool this is. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original and to each other. So here we go. We start out with a big right triangle, and this first sentence says, if the altitude is drawn to the hypotenuse, so that is this altitude right here. If you draw that in, you create two little right triangles that are similar to each other and to the big one you started with. So it's pretty neat. Down here in this little diagram that I've created for you, right here, check this out. So I got, let me separate. So there, let me spin them for you so you can kind of get a good picture of what's happening. Spin this bad boy, then I got to flip it. So check this out. There you have the three triangles all oriented in a fashion that will show you, there, let me mark it for you too. So each one of these triangles has a right angle, a little single loop, and a little double loop. And you guys know from chapter 8 that you have angle similarity once you have two angles matched up. So that's really why this works. They all have a right angle, and then they all have another angle, in this case both angles, but all it needs is one to give you that AA similarity. So whenever you have that scenario where you have a right triangle dropping the altitude to the hypotenuse, you bust it up into three little or three total similar triangles. So now the first problem is just identifying. So your first problem on your quiz will just be like, hey guys, identify the similar triangles in the picture. So I blew it up for you here a little bit, and this is usually how I do it. Like some people like to separate and redraw them. Your book will talk about that if you want to watch that video, but I think it's easy just to mark it. So here's how I roll with this. I go like, all right, I got my big triangle. It already has the right angle down here at T. And so what I'm going to do is give one of the angles, like S, a single loop, and then R, I'll give a double loop. So now all three of these triangles are going to have a right angle, a single loop, and a double loop. So check it out. The little triangle on the right. Well, here's its right angle. So it will be continued on to the other side as well. So I'll just put it over there. And so now it already has a single loop because I did it in the beginning. So then that means it's going to have a double loop for its other angle. So now the little right triangle on the right, SUT, it has a single loop, a double loop, and a right angle. Now the one on the left, it has a double loop over here at R. It has its right angle at U, and now it needs a single loop. So that's going to be at T. So the confusing thing you can see here is T. T is a right angle for the big triangle. It's a single loop for the left-hand triangle and a double loop for the right. There's three different angles at T that are happening. So now when you list it, watch how I'm going to roll with this then. I'll start out with my first one, triangle. I'll just go alphabetically, R, S, T. Doesn't really matter how you set up that first one. But now when you do this one, or either the next two, let's see, let me do the one on the left first, so RUT. So the R, if you go with it like this, so I started out with my green double loops, and then S was my blue angle, the single loop, and then T was my right angle. So then I need to do that for all three of them, right? So my next one, the little one on the left, let's see, R, the double loop, so R is going to be first in that one as well. And then the S in the big one is the single loop. That's going to be the T in this one, that's this angle right here. And then the right angle that I had T in the first one will match up with U in this one. All right. And then let me just double check. So I started out with my double loops, my green, and then I went to my single loop. S in the big triangle was the same as T in the one on the left, and then the T in the big one, the right angle, is the same as the U in the medium-sized triangle. All right, so let me go back to doing this last little one now on the right. So the single loop, or the double loop was first, R and R. So the R in the big one and the R in the one on the left will match up with the T in the one on the right. And then the S, let's see, the single loops, that's going to be an S in the little triangle on the right. And then, of course, the right angle is last, so S or T, then S, then U. So let's just double check. So first was my double loop, double loop, double loop. Yep, that's right. And then my green ones, then my blue ones. And the big triangle was S. And the one on the left was T. And then in the one on the right, yep, it's S again. And then in red, I had all my right angles. So T in the big one, U in the medium one, U in the small one. So just match up. And again, the order of these first three, that's up to you. On a quiz, typically, in class anyway, I would have these three already started for you so that you can match up the other two. On a computer, it'll be even easier for you to match them up. All right, so go ahead and pause it here and then pick it back up for the monitor progress. All right, so monitoring progress, hopefully you got this one, guys. And again, you might have this order different. I just went QSR, no particular reason. And then, so hopefully you match it up. If you went like RSQ, for instance, or QRS, then adjust accordingly. Split the Q should match up with the S in one, the Q in the other, S with T and T, R with R and S. All right, moving on to geometric mean. Now you heard the word mean before. You've seen it back in the day. Typically, though, what you dealt with was an arithmetic mean, which is like, hey, let's add these two things up and divide by 2 to find the average of something, the mean. Well, there's another type of mean in the world of mathematics, and that's a geometric mean. Now, when you take Algebra 2, you'll discover a little bit more of where this comes from. It's typically just, let me just real quick, because I love it so much, I have to tell you about it. If you had a geometric sequence, so a sequence that multiplies the same thing every time. All right, so if I was doing this, multiplying by 3 every time, well, how would you find the mean of two numbers? Say we didn't know what this was, and we wanted to find what that x would be right there. And I know it's multiplying by 3 every time. Now, you could probably figure this out in your head logically, but if it's decimals or fractions or crazy numbers, how would you do it? Well, that's where a geometric average comes from. And instead of adding two numbers and dividing by 2, you're going to multiply these two numbers that surround it and then take the square root. So for instance, in the book, they tell us that if we want to know the geometric mean of two positive numbers, a and b, then we multiply a and b together and then take the square root. So you don't have to do all this every time or this or blah, blah, blah. Like for instance, in example 3, if I see what's the geometric mean between 8 and 10, then I know I can go straight to, it's going to be the square root of the two numbers multiplied together. All right. And then of course I can simplify that. That's going to be the square root of 80, which breaks down into 16 times 5, which is 4 roots of 5, since I can't break 5 down any further. So a lot of radicals with this stuff because you're taking the square root of the product of the two numbers. So keep that in mind. You're going to be reducing radicals a lot. If I were to do it up above here with the problem that I presented with you guys in the beginning, you'd be like, all right, well, what's the square root of 3 times 27? And that's 81. So square root of 81, of course, is 9. 9, of course, would be your missing number. So that's where it's coming from, geometric sequences, geometric mean. And try the monitor progress here. Pause the video. See what you guys come up with for monitor progress number 5. All right, so back again. This one hopefully was pretty easy. Square root of 4 times 9, which is the square root of 36, which is 6. All right, so if you were going to multiply 4 by something to get to 6, it'll be 1.5. And then you multiply by 1.5 again to get to 9. So it's kind of like you had that sequence like 4, I don't know, 9, and you're multiplying. 6 would be the thing that you'd fill in the blank with. But for you guys, it's like super simple in geometry. Like you can just cut straight to square root of 36, boom. All right, moving along. Now this is the main part of the lesson here today, guys, is how you can solve for missing sides of these right triangles in this situation whenever you have a big right triangle and then you drop the altitude to the hypotenuse. All right, so just like the scenario we saw in example 1. Now you can actually solve when things are missing. And a lot of words in this paragraph up above. Because the right triangles are similar, essentially what you're doing is setting up proportions for these. You're like matching up small leg to small leg, big leg to big leg, hypotenuse to hypotenuse. But it's way simpler than trying to think through all that all the time. These two theorems here will help guide you in setting up equations to solve for things. Now, the first theorem tells you that the altitude can be a geometric mean. So in this case, it is CD. So what's that mean if you're a geometric mean? Well, it just says, all right, I can be on the left-hand side of an equation squared, and what's it the mean between? That's really what you have to memorize. And so it's the altitude is the mean between the two little pieces of the hypotenuse that it breaks it up into. So like in the example that we just had when it said 4 and 9, like it could be potentially like that is your 4, that is your 9, and then your answer would be your 6, like the monitor progress question we just did. So the first place a geometric mean could be in this situation is CD, all right? And then the other theorem is for the legs. Now it's the legs of the original big right triangle. So in this case, we've got the triangle ABC is the original triangle, and it has two legs, of course. So it's got CB. So CB can be a geometric mean, and CA or AC can be a geometric mean. So now, what is it the mean between? Well, here we go. If it's CB, it's the mean between the little piece of the hypotenuse that it's across from, in this case DB, and then the whole big hypotenuse, which is AB. So that's giving you this first equation here. And then if you're dealing with the other leg, then that's going to be the mean between the little piece of the hypotenuse it's across from and the whole big thing. So in our example that we had before, it'd be like, all right, if this was 4 and the whole thing is 9, then this would be your 6. So you're just taking the two things that it's the mean between, multiply them together, and then you take the square root. That sounds a lot of words, guys. Don't get freaked out yet. The examples will help you so much. So let's get into it. All right, so in example 4, I'm looking at this. Now, I just know from doing this for a million years, here's my altitude drawn to the hypotenuse. So I know that's the mean between 6 and 3. So when I set it up, I just go x squared equals 6 times 3. So when you take the square root, x is the square root of 18. And of course, that can get busted up into square root 9, square root 2, which is 3 roots of 2. Now, how did I do that so fast? Well, just because I remembered this, the theorem from the page before, the geometric mean altitude theorem, because I was dealing with an altitude. I was looking for an altitude. Now in part B, I switched tracks, and now I'm looking for one of the legs of the original big right triangle. So I think back to this theorem, the geometric mean leg theorem. It tells me, well, a leg, so y squared, is the geometric mean between the piece of the hypotenuse it's across from, so 2, times the whole big hypotenuse, which in this case is 7. So now I'm like, whoa, y squared equals 14, square root, and I can't do anything with that. 2 and 7 doesn't help me to break it down because they're not perfect squares, so you're just done at the square root of 14. All right? No, again, a lot of words, but it all comes back to these two theorems, and you'll be able to recognize things the more and more you practice. All right, example 5 puts a little twist to it, but it's still the same concept. I am looking at this picture here. Now they give me the altitude to the hypotenuse, and I'm missing one of the little pieces of the original hypotenuse that it got busted up into. So same process though, guys. My geometric mean is 8.5, is the altitude to the hypotenuse. So my left-hand side is going to be 8.5 squared, and then it's going to equal the two little pieces of the hypotenuse that it gets busted up into, 5 and w. So 5 times w. All right, so 8.5 squared, 72.25 equals 5w. Now in this one it says approximate the height. So that's how I know I'm just going to be able to just get a decimal for this one. And when I divide both sides by 5, I've got 14.45 b and w. All right, so that would be the missing side, the missing piece of the hypotenuse. All right, go ahead, pause the video here, and try your last mantra progress, my friends. All right, so hopefully you got a little something like this, my friends. You got x, there's your altitude, so it's the mean between 4 and 9. Again, it's that same example of numbers we've been having. So x is 6 in that one. Now over here, 12, it's a leg of the original, so it goes on the left-hand side by itself squared. So 12 squared equals the piece it's across from and the whole big hypotenuse. So 9 times x. So 144 is 9x, so x is 16. If they asked you for this little piece over here, you could just subtract 16 and 9. If they asked you for that leg over there, now you could use Pythagorean theorem. But you can see it's going to open some doors for a lot of interesting things for us. So if it's confusing, stick to these examples. The homework will stick to these examples as well. And again, ask me if you have any questions, my friends. All right, peace.